Welcome to Chapter 10, Intertemporal Choice. The Intertemporal Choice chapter is more or less a review of everything we've done in the variant text up to this point. The first element that we did was the conventional consumer choice problem. You remember we started with that first sentence in Chapter 2. Economists assume that consumers choose the best bundle they can afford. That was choice, right? We assumed that consumers chose from two consumption goods, and we married their indifference curves to their budget lines and modeled choice. Revealed preference was where we turned the choice model on its head. Remember, the choice model started with the assumption of what consumer preferences were. Revealed preference, we observe consumers' choices and then infer from that what their preferences must be, or at least boundaries on their preferences. And finally, in the Slutsky equation chapter, what we did is we decomposed the effects of price changes into income and substitution effects. Now, we're going to combine elements of all three of these in the chapter on intertemporal choice. To more formalize this correspondence, I wanted to first remind you of all the elements of the conventional choice model that we have developed so far in the course. You recall that Varian made the simplifying assumption that we have two consumption goods, and Varian denoted these in his dry textbook notation as X1, X2. We talked about going to lunch at VTEX and eating gut packs and drinking Dr. Peppers. Preferences, you remember, showed the rate at which consumers were willing to trade one good for the other good while maintaining the same level of utility. Income was assumed as given, but we had, this was the amount that could be spent on the two consumption goods. We combined all this information with the budget equation, and you see the conventional form that we have talked about at great length, P1x1 plus P2x2 equals M. And finally, you remember what we could do is we could reorder that budget equation and express the vertical variable as x2, the horizontal variable as x1. We could rearrange this equation to isolate x2 on the left-hand side, put everything else on the right, and then we got an expression for the slope of the consumer's budget line. And that was negative P1 over P2. In the world of intertemporal choice, the consumption goods now become consumption in time period 1 and consumption in time period 2. You could think of these as aggregate amounts to spend within each time period. And then presumably those consumption amounts would break down into the various consumption goods that were chosen in each time period. But to illustrate the problem of choice over time, or intertemporal choice, we can just measure composite consumption in each time period, C1 and C2. The consumer is also presumed to have preferences over choices for consumption levels in time period 1 and time period 2. Do they insist on fixed proportions? Are they willing to substitute some for the other? Are they perfect substitutes, right? Income is going to be a little bit different. Income can be earned in each time period, right? So we have period 1 income and period 2 income. We can move those dollar amounts from the future into the present by borrowing, or we can move income from the current time period into future time periods by saving. And this is illustrated by the budget equation. So you remember the conventional form of the budget equation, which I have on the left. We have prices for time period 1, prices for good 1 and prices for good 2. In this intertemporal budget equation, this expression that I have here is relative to the first time period, right? So relative to time period 1, the price of consuming $1 in time period 1 is 1. So there's the implicit 1 for the price of consumption in the first time period. The time period 1 price of consuming $1 in time period 2 is 1 over 1 plus R, which you'll find in, I believe it's the next slide, is the discount rate. Right? So time period 2 consumption is discounted to the present. Time period 2 income is discounted to the present. So this budget equation here is relative to time period 2. We could write the budget equation relative to time period 2, right? So then if it were written relative to time period 2, the time period 2 price would be normalized to 1, and the time period 1 price would be 1 plus the interest rate. Now, if I take the budget equation as written on the right-hand side, I can rearrange it to get the slope of the budget line, which you see becomes minus 1 plus the interest rate. This is the rate at which the consumer can transfer income between time periods, whether that be through saving or borrowing. Now, Varian has made the simplifying assumption that the consumer pays the same interest rate whether they are saving or borrowing, which, of course, we know that's not true in real life, but we make the simplifying assumption. The discount rate, as I said in the previous slide, is 1 over 1 plus R. It's, in essence, the first period price of $1 spent or earned in the second time period. The reason why this is the appropriate discount rate, you could think if I invested the amount 1 over 1 plus R for one time period and received an interest rate of R, at the end of that first year, I received my principal back, which is 1 over 1 plus R, and then I would receive the interest earned, which would be R over 1 plus R. I combine those together, and I would get 1 plus R divided by 1 plus R, which would be 1. So 1 over 1 plus R is the amount that I would have to invest for 1 year to receive $1 at the end of the year in combination of interest earned and the principal return. So that's the appropriate discount rate. I'd first like to consider the case of a saver. So a saver is someone who in time period 1 consumes less than the amount that they've earned in time period 1. So you can see that illustrated in the graphic on the left-hand side. On the horizontal axis, you see M1, and then to the left of it is C1. So this consumer is spending less in time period 1 than the amount of income that they've earned. And that's what makes them a saver. And the amount of their savings, of course, would then be M1 minus C1. And that savings then allows them to consume in the second time period more than their time period 2 income. So the excess of consumption over income in the second time period, that's C2 minus M2, is equal to the amount of savings, which is C1 minus M1, times 1 plus the interest rate. So the balance that was deposited can be spent, and the amount of interest earned can also be spent. So this is what describes the situation of a saver. Now, consider what would happen if this consumer who was a saver faced an increased interest rate. We can use the tools of revealed preference to get an idea of how this interest rate increase affects the saver. Notice that the budget line with an increase in the interest rate it pivots around M1, M2, right? So an increased interest rate means that this consumer has, all else equal, less funds available that they could borrow in time period 1. So consider the horizontal intercept. That's the maximum amount that the consumer could spend in time period 1 if they borrowed every penny that they could from time period 2 consumption. So if they made a commitment not to consume anything in time period 2 and borrowed every last penny and spent it in time period 1, that's what the horizontal intercept represents. So you'll notice that the green budget line shows that with a higher interest rate, the consumer would not be able to spend as much in time period 1 if they had the maximum possible consumption. Likewise, if the consumer spent nothing in time period 1, saved everything, and then spent it all in time period 2, that maximum possible time period 2 consumption is given by the vertical intercept. So you'll notice that the increased interest rate makes it possible for the consumer to spend more on time period 2 consumption if they were to max that out. The pivot point is at M1, M2. That's where there's no borrowing or saving. So what we can say then is, in the first time period, that's represented by the black budget line, our consumer was observed to choose point C1, C2. We know through the tools of revealed preference that C1, C2 is directly revealed preferred to any point on the black budget line or underneath it. And remember, the more informal language to describe that was that C1, C2 was the best bundle that the consumer could afford, right? So if preferences, which we don't know, were presumed to be strictly convex, that means that the indifference curve would be tangent to the black budget line at C1, C2. That would imply that C1, C2 was the best possible bundle this consumer could afford. Any other point is worse. So we can say categorically that the increase in the interest rate has made this saver better off. The reason why is when we decompose what the changes made to the consumer's budget set are. We know that this pivoting of the budget line makes the old consumption point C1, C2 interior to the new green budget set. If the old point now is interior to the new budget set, that means the consumer could afford potentially more time period 1 consumption and more time period 2 consumption. They could afford more of everything. And since both time period 1 and time period 2 consumption are monotonic, meaning more is better, the consumer has been made better off. The points that have been deleted from the budget set, so those are points to the southeast of M1, M2, right? So that sliver, that triangle that's bounded from above by the black budget line, from below by the green budget line, southeast of the point M1, M2, I claim that those points are worse than C1, C2, right? Because remember, C1, C2 is directly revealed preferred to those points. So we've eliminated points from the budget set that are worse than the original consumption point, and we've enabled the consumer to buy more of everything. They're unquestionably better off. The other thing that we can say with certainty is that this consumer who started as a saver will continue to be a saver after the interest rate increase, right? So to become a borrower, they would have to move to a point that's southeast of M1, M2. If they did that, they would violate warp, right? So we don't want that. Consider a saver who faces an interest rate cut. I've illustrated this with a red budget line. So it turns out that we can't really say much in this situation. We're uncertain how the interest rate cut affects the saver. And the reason is that C1, C2 is no longer affordable under the red budget line, right? So we get this pivoting of the budget line again. C1, C2 is now no longer part of the budget set, but the consumer has new combinations of C1, C2 they could afford now that they no longer, or that they couldn't under the original black budget set, right? Those would be points where the saver would have to become a borrower. And we don't know whether those are better points or worse points. So that contributes to the uncertainty, right? The deletions from the budget set, so that would be the triangle to the northwest of M1, M2, right? Those deletions are inferior to C1, C2, right? Because C1, C2 was directly revealed preferred to those choices. So the deletions are worse, the additions may be better, they may be worse, we don't know. So taken together, that means we're uncertain how this interest rate cut affects the well-being of the saver. So as a result of all these things, we're uncertain whether this saver would continue to be a saver or whether they would change their ways and become a borrower. We just don't know. Now, consider a consumer who is a borrower. So a borrower is someone who borrows from their future income to fund additional consumption in the present. So since time period 1 consumption exceeds time period 1 income, that necessitates borrowing. Right? And since they are borrowing from future income, what that means then is time period 2 consumption has to be less than time period 2 income. And then I have finally the budget constraint, right? So C1 minus M1 is the excess consumption over income in time period 1. That is equal to the discounted amount of unspent time period 2 earnings. Right? So M2 minus C2 is what the consumer doesn't spend in time period 2, then that's discounted to the present. So that is the amount of borrowed funds that are available to the consumer to fund excess consumption in time period 1. Now we consider an interest rate increase for the borrower. So again, we get this clockwise pivoting of the budget line around the endowment point M1, M2. And much like the last slide we considered, there's a great deal of uncertainty in this case. We're uncertain whether the borrower is made better off or worse off by this. And the reason why, again, is that the original consumption point, C1, C2, is now no longer affordable, and the consumer has new combinations that are available to them. That's in the northwest corner, and we don't know whether those points are better off or worse off. Would make the consumer better off or worse off. And furthermore, we're uncertain whether the borrower will remain a borrower when the interest rate increases, or they might become a saver to get to those new points in the northwest. The punchline is we really can't say much about how the consumer would be affected, their well-being would be affected, and whether they would continue to borrow or become a saver. If we have someone who is a borrower and they face a cut in the interest rate, we know that the borrower will be made better off. The reason why is their original consumption point, C1, C2, is interior to the new budget set, represented by the green line. And the points that are deleted from the budget set, the triangle to the northwest of M1, M2, are points that are not as good as C1, C2, right? So we've added points that are better by monotonicity. We have deleted points that are worse by revealed preference. So we know that the borrower is made better off by an interest rate cut. Much for the same reasons, we could say that the saver was made better off by an increase in the interest rates. We can also say the borrower will remain a borrower after the interest rate cut, right? Because if they were to become a saver, that would move to a point that's interior to the original budget set, and those would be worse than the original consumption point C1, C2. And that would violate warp, so that's not going to happen. We can use the Slutsky equation to make further statements about the consumer's behavior. This is the calculus version of the Slutsky equation. And let me say first, before we dive into this, that the Slutsky equation is built around the time period 2 budget equation. So you remember the budget equation, as we described it before, what we did is we discounted time period 2 consumption and income into the current time period. The future budget equation would be where I move time period 1 income and consumption into the second time period. So P2 in this case would be 1, and P1 would be 1 plus R. That would be, in essence, the price, the time period 2 price of $1 of consumption in time period 1. Okay. So the Slutsky equation tells me what is the total change in time period 1 consumption as we change P1. And P1 is 1 plus the interest rate. So in essence, what we can say then is this is how time period 1 consumption changes as we change the interest rate. The first term of the Slutsky equation, you remember, was the substitution effect. The substitution effect was the partial derivative of the compensated demand curve with respect to the change in price. The compensated demand curve, you remember, was we hold the consumer's purchasing power constant and then hit them with the new price. Right? So we look at purely the effect of changing prices, holding purchasing power constant. And you remember that was globally negative. We established that in Chapter 8 with the Slutsky equation. So what this is saying then is that when the interest rate rises, the consumer is going to substitute out of the expensive good, which now is time period 1 consumption, and into the cheaper good, which is time period 2 consumption. So that means the first term, the substitution effect, is globally negative. The second term of the Slutsky equation, the partial of C with respect to M, you remember when we initially did the Slutsky equation, this was the one that was kind of complicated because we said that the sign of this one depended upon whether the good was a normal good or an inferior good. A normal good, you remember, is a good where as I become wealthier, I want more of it. And an inferior good is a good where as I become wealthier, I want less of it. Well, consumption is a normal good, right? Consumption in period 1, consumption in period 2 are both by assumption normal goods. So that makes this term globally positive. We multiply it by the next term, which now is where the complications come in. M1 minus C1. This term is going to be negative for a borrower, right? So a borrower, you remember, borrows from future income to fund current consumption. So C1 is greater than M1. So for a borrower, M1 minus C1 is going to be negative. For a saver, they consume less than their available income in time period 1. So that term will now be positive. So in the final column on the right, what I've done is I've attempted to sign this equation for both borrowers and savers. What I can say is for borrowers, that's the first line, the third line in that matrix. The substitution effect is negative. We add to it the positive income effect times the negative sign, the term that's negative, M1 minus C1. So a negative plus a positive times a negative. A positive times a negative is globally negative. So we have negative plus a negative. The Slutsky equation is negative for a borrower. But when the sign on that third term flips, what I can say then for a saver is that we're unable to sign this Slutsky equation for savers, right? So what this means literally is that when the interest rate rises, a borrower will choose to consume less in time period 1. Let me state that again. For a borrower, increasing the interest rate causes the consumer to consume less in time period 1, right? So a borrower, you remember, borrows from future income to fund current consumption. If the interest rate rises, that becomes more expensive, and the Slutsky equation is telling us unambiguously the consumer will do less of it. That makes perfect sense. For a saver, though, the net effect is ambiguous. It depends upon whether the substitution effect, which effect is larger, the substitution effect or the income effect. Let me go back here. Yes. So what we're seeing here is a saver who faces an increased interest rate. You recall this was the case that was ambiguous. We're uncertain whether time period 1 consumption increased or decreased. What we were able to tell through revealed preference is that the saver would continue to be a saver after the interest rate increased. So what that means is that C1 can never rise above M1 when we face an increase in the interest rate. But what the Slutsky equation is telling us is we don't know whether C1 increases or decreases, right? We have an upper boundary of M1, but it can either increase or decrease. What we can say for the borrower is that C1 must decrease, right? So through revealed preference, remember we really didn't know much of anything, right? We didn't know whether the borrower is made better off or worse off by the increase in the interest rates. We don't know whether the borrower would remain a borrower or become a saver. What the Slutsky equation tells us is that C1 must decrease as a result of increasing interest rates. So the question is, by how much? That determines whether the consumer continues to be a borrower or becomes a saver as a result of the increase in the interest rates. Okay? Discounting. Now, to amplify on this topic of discounting just a little bit more, so far we've assumed away inflation. So if a consumer saves, right, so that's this first little bit of math. Suppose we have a consumer who funds additional consumption in the second time period above their time period 2 earnings through savings. You remember the way we expressed this before is that the consumer is able to spend their principal and they're able to spend their interest received. If we also adjust for inflation, what we could say then is that if time period 2 nominal prices were to rise, if we were to adjust for that increase in the general price level, we should divide this by 1 over 1 plus pi, where pi is the rate of inflation. What this means then is that 1 plus r over 1 plus pi is equal to 1 plus the real interest rate, rho. And oftentimes in introductory econ classes, the real interest rate, rho, is approximated as 1 plus the the real interest rate, rho, is approximated as the nominal interest rate minus the rate of inflation. Okay. The British government gave this, they issued this very interesting security back in, I believe it was the mid-1800s. This is the sort of thing that only the British government would do. Right? The American government, when they fund their debt, the Treasury bill, the typical way of doing it, is a promise by the U.S. government to pay the bearer a certain amount of money in 90 days. Right? Not so much now, but at least the federal government used to give 30-year bonds, right? So the government would give an annual payout of interest and then refund the principal in 30 years. The British government issued this debt that actually didn't have a maturity date. So it was literally a promise to pay £1 or some certain fixed amount every year forever. And that was called a consul. So if we wanted to figure out how much a consul should sell for in the marketplace, suppose that we have this security that pays £1 annually forever. The present value of that, we would take the first payment of £1, which occurs a year from now, and discount it to present. The £1 that's paid 2 years from now discounts to present by being divided by 1 plus the interest rate squared. And then we have the third period and so on and so forth forever. Now, you might remember in one of your math classes, I remember certainly seeing this in calculus and probably even algebra 2, this idea of summing an infinite geometric series. So if you can express some infinite sequence as as ever higher powers of a base, and the base here is 1 over 1 plus r, as long as that base, the absolute value of the base, is strictly less than 1, an infinite geometric series sums to a finite amount. So in the second line, what I've done is I've shown how if I factor 1 over 1 plus r out of this present value, I get a well-defined infinite geometric series. So the infinite geometric series starts with 1, which is the base to the 0th power, plus the base to the first power, plus the base to the second power, and so on and so forth. The sum of an infinite geometric series is equal to 1 divided by 1 minus the base. And the base of this geometric series, remember, was 1 over 1 plus r. If I manipulate this a little bit, and simplify it, it turns out that this infinite geometric series can be simplified. The sum of it is 1 over the interest rate. So, for instance, if the interest rate today were 5% and it was assumed to remain 5% into perpetuity, the present value of this promise to pay £1 annually forever would be 1 over the interest rate of 0.05 or 20, right? So this security should sell on the open market for £20. We also need to take account of taxes and interest income received. So if I save money and my bank pays me interest, that interest income is taxable income, and the government will tax it at the marginal tax rate. And just to be general about it, suppose that that's T. So what we could say then is that the consumer, when they save $1, the amount that increases their spending in the next year is not 1 plus the interest rate, but it's 1 plus the after-tax interest rate. The after-tax interest rate would be the interest rate times 1 minus T, where T is the marginal income tax rate. So, for instance, just to make the math easy, if I were in the 25% marginal tax bracket, what that says is that the increase to my purchasing power by saving is, after paying taxes, is 3/4 of whatever the interest rate is. Certain forms of borrowing, interest paid, is also tax preferred. One of the bigger ones, the ones that will be more relevant to you, hopefully within the next 5 to 10 years, would be if you buy a house. The interest that you pay on your mortgage is tax deductible. What that means is if you pay $1,000 in interest, that reduces your taxable income by $1,000. So if you were in the 25% income tax bracket, what that means is paying $1,000 would reduce your tax liability by $250. So if you paid $1,000 in interest, it reduces your taxes by $250. That means your net expenditure is really $750. So the after-tax interest rate, at least on mortgage interest paid, is also the interest rate times 1 minus the marginal tax rate. On to the quiz. The first problem we'll consider is problem 3. And Mr. O.B. Candle of problem 10.8. So remember, again, these references, 10.8, this would refer to the old paper intermediate micro workbook by Bergstrom and Varian. So Mr. O.B. Candle has a utility function C1, C2. So Mr. Candle is Cobb Douglas. He has no income in time period 2. He has an income of 70 grand in time period 1, and he faces an interest rate from 10% to 13%. Oh, before we launch into this, if Mr. Candle has no income in time period 2, what that means is he must be a saver, right? So he has to save a certain amount in time period 1 to fund his time period 2 consumption. Now, what we know is that since OB is Cobb Douglas, we can apply the exponent rule to him and see instantly that he will spend 1/2 of his income on period 1 consumption, 1/2 of his income on period 2 consumption. So that means he will, and then since there's no income in time period 2, raising the interest rate does not affect the present value of his income stream. So he continues to have $70,000 of income. He will spend half of it on period 1 consumption. That's 35 grand. He will save $35,000, invest it, and then the principal plus the interest is what funds his time period 2 consumption. So the $35,000 that he saves initially was invested at 10%. Now it's invested at 13%. So his time period 2 consumption goes up, but his time period 1 consumption, his income, his savings all stay the same. So I can see working through this that the only answer that's consistent with all this before we even do any math is B. B has to be the correct, or maybe I should say B is the only response here that has the potential of being correct. Okay. Now we can do the calculations. So we apply the exponent rule. We know that his savings are $35,000. The interest rate went up by 3%. So what we can say then is that his increase in time period 2 consumption would be 3% of his savings amount, which was 35 grand. So his time period 2 consumption rises by $1,050 and everything else is the same. Problem 5, we have a village that has a corn harvest. No, sorry, this is just grain. I shouldn't presume corn. But we have 6,000 bushels of grain that are harvested. And next year, the harvest will be 1,100. If rats eat 10% of any grain that's stored for a year, how many bushels of grain could the villagers consume next year if they consume 1,000 bushels of grain this year? Well, I just guess to go straight to the math, if they consume 1,000 bushels this year, what that means is they're saving 5,000 bushels. Because remember, the harvest the first year was 6,000. They consume 1,000, 5,000 are saved. And this is actually a negative interest rate, right? Because the rats eat 10%. So what that means is if they store 5,000, 4,500 bushels remain next year to be consumed because the rats are going to eat 500 pounds. So the maximum time period 2 consumption is going to be the 4,500 bushels that are saved that the rats didn't eat, plus the time period 2 harvest, which was 1,100 bushels. So the maximum possible consumption is 5,600 bushels.